Okay, good. We are recording. That's good. So, yeah, so we are Newtonian mechanics. So, what was the setup? So, we have this base Rn plus Rn star. We just think of it as R2n. Although, I mean, this is eventually going to be very risky. We should not identify the dual of the space in general, the space, but in this case we do. This is the phase space, as you remember. Okay, and then we have this Hamiltonian H. Yes, H from R2 and R. So we just use coordinates. So this is the space. This is position and momentum. Okay, right? And we have this Hamiltonian. And then Hamilton's equations of motion, the dynamics was these equations. So these equations were like this: Q I dot equal to PH dPi, and PI dot is equal to minus PH dQ. So one of the things I promised to do was to prove Liouville's. I mean, okay, so here is an example. The typical example is H of Q and P. I just don't write QI and PI, I just write Q and P is Q2 over 2n plus B of Q. So this is kinetic. And this is the potential energy. So the idea is that this Hamiltonian always represents energy of the system for us as a function. Yeah, okay, so these are two first order actual questions. So one of the things I promised to do was Liouville's volume theorem. I mean, basically, it was that the volume is preserved under the flow. So the Hamiltonian flow preserves the volume. So this volume is so yes, okay, so I mean it's clear. So we have this domain D, and so let's denote the flow by phi t, and this turns into some other domain. This is phi t of t, and this the volume of this D and volume of phi t of t are the same for all t. And the way to see this is actually it's a special case of a much more general statement, which I want to get to that statement, more general statement. So proof is a corollary of a more general theorem that I'm going to discuss now. So we're going to forget about this mechanics or everything, just go back to the world of calculus and analysis and geometry. So what's the situation? So we look at this space Rn, and imagine you have a vector field on Rn. So we just always got a vector field as some xi, e, xi, I from 1 to n. We have a vector field. And to this vector field, we can attach a function which we call its divergence. So divergence of x is a function which is sum d xi d little xi I from 1 to n. So it's a function, right? It's the divergence function. It's a generalization of divergence function of vector analysis in 2 and 3 dimensions. Yes. Okay, now we can do another thing with this vector field. We can define a differential equation also using this vector field. So the differential equation is xi dot equal to xi of x1 xn. So I between n. So this is an autonomous first order differential equation. So the vector field in Rn defines this differential equation, and then this differential equation is locally solvable. So in other words, if you take any point, there is a unique integral curve. There is a unique solution that passes through, that goes through the space, and at each point, the tangent space to this curve, actually the velocity of the curve is exactly the vector field at that point. So this fills the whole space with these integral curves with solutions of the thing. So this point, for example, x0, then if you follow it by time t comes to the point which we denoted by phi t of x0. And then you do this for the whole point, you get so let's assume that actually is the solution curve exists from -infinity to +infinity. I mean, in nonlinear system, usually it's not the case. Usually they blow up in finite time. You just hit some singularity. Not singularity of vector field, but the differential equation solution cannot be continued up to infinity or -infinity. But let's assume that it can be. For example, in the case of linear systems and some other systems, this is the case. Let's assume that's the case. So then, basically, from this vector field, you get this phi t belonging to R. So this is a one-parameter group of diffeomorphisms of the space. You get it. It's a one-parameter group of diffeomorphisms. Okay. Now, we want to study the action of this one-parameter group of diffeomorphism on the volume form. So how it moves the volume forms. So in other words, we want to see how this diffeomorphism changes the volume in space as it moves. So the lemma is this. That omega be equal to dq1 with, oh no, not dq, sorry, no, I'm in general, dx1 with dxn, oh, capital N, sorry. This is the volume form of our N. Then ddt of phi t star of omega at t equal to 0. So you have this N form, you pull it back under phi t, and you compute the derivative of this one form phi t at t equal to 0. So this is going to be again an N form. So this N form is actually given by divergence of x of phi divergence. It's going to be divergence of x times omega. So the fact that it is a multiple of omega is not a surprise because it's an N form anyhow. So it has to be a multiple of omega. So that's not. But the interesting thing is that the coefficient is exactly divergence of x. So in other words, divergence of x measures the infinitesimal rate of change of volume. So i.e., divergence of x measures both the infinitesimal rate of change. So now the proof, so of course, also from divergence theorem, we know that divergence has something to do with volume anyhow. And this is one connection. So proof, there are several proofs of this. I give a maybe more high-tech proof using differential form technology, which is good to know anyhow. So first of all, we call the derivative x of omega. So the lead derivative of a tensor field with respect to any vector fields can be defined. You just look at the, this is really just ddt of phi t star of omega at t equal to 0. I mean, this is really, the left-hand side of the equation is really just definition of lead derivative. What does lead derivative mean? Lead derivative means that you draw the integral curves of the vector field and you study the variation of the tensor field along that integral curve. You take its derivative. So that's the lead derivative. Okay, so there is a formula for lead derivative, which is really a wonderful formula. It's called Cartan's, sometimes it's called Cartan's magic formula. Really an amazing formula. It just says that Lx is equal to Vix plus Ix. Ix is interior multiplication. V is exterior derivative. So this formula is essential. So if I apply this formula, then I get that Lx of omega equal to Dix plus Ixd of omega. Now, this part, of course, drops because omega is an n form. So on n-dimensional space, so its differential is 0. So there is no term here. And so this remains only Dix of omega. So we have to compute only this part. Dix of omega. Now, what is that? So let me give an example. Imagine n is equal to 2. Let's look at a simple example. So the vector field in this case is x is equal to x1. Oh, yeah, x1 of x1, x2, ddx1 plus x2 of x1, x2, ddx2. So we have that. Now, when you want to compute Ix and omega, so here, Ix of omega is equal to x1 I ddx1 of omega plus x2 I ddx2 because x1 and x2 are just scalars, they come out, and when you substitute, you just get. So now what is that term? Let's look at this term. So what is interior multiplication with respect to dx1 of dx1 wedge dx2? Well, we're supposed to act this on that, and then we just keep the x2. So this is equal to, and this is dual to this one. So when you evaluate this one for over this vector field, you get 1, because this is dual. So you remain with the x2. Okay, and then by the same token, if you compute dx2 of omega dx1 wedge dx2, now this has to go inside, so you pick a sign, and then it becomes minus dx1. Okay, so then it means that this is really nothing but x1 dx2 minus x2 dx1. Right? Okay, now we have to compute the d of this term. x1 dx2 minus x2 dx1. What is that? Well, this is partial of this dx1 wedge dx2, and notice that the dx2 part cancels with this. It's 0. And in the second component, you get there's a minus business going on, so you pick up plus sign. So then this becomes plus dx2 dx1 wedge dx2. And you see that this is equal to divergence of x dx1 wedge dx2. So this is the proof for n equal to 2. In general, the same thing happens. You see the pattern now. In general, the same thing happens, and in general, so it's easy to repeat this. Okay. So this is a very interesting formula. And now let's go back to Hamiltonian things. So there is a vector field, right? In that case. So we have this function h of q and p, and we attach to this vector field xh, which is the vector field is sum dh dpi d so ddqi, and then minus dh dqi ddpi. This is exactly the vector field that goes to the right-hand side of Hamilton's equations. if you think of Hamilton's equations, we have this Qi dot equal to dH dPi, and Pi dot equal to minus dH dQi. Exactly. This vector field appears on the right-hand side of Hamilton's equation. Okay, now this is called Hamiltonian vector field. So we are going from functions to vector fields. You see, this is the process here from functions on phase space to vector fields on phase space. And this is called, so send H again to H. So this is called Hamiltonian vector field or symplectic gradient. It's also called symplectic gradient. Because it's a special case of something more general that we call symplectic. Okay, so anyhow, what you notice is that divergence of this is always zero. If you look at this vector field, its divergence is zero. It's trivial to see, right? No. Divergence of X A is I mean, what happens is that in fact, you get divergence of XH, you get sum d2h dqi dpi minus sum d2h again dpi dqi, and they cancel, so it's zero. So that's so this is a divergence-free vector field, right? So this is a divergence-free vector. So this immediately shows that. So now volume preserving property. So we want to show that for any D inside R2N, some bounded open nice subset, the volume of D, we want to show that this is equal to volume of phi t, the Hamiltonian flow phi t of D, right? We want to show this, right? But what is volume of phi t of D? This is just by change of variable formula in multiple integrals. This is equal to integral over D phi t star of omega. We just put back the volume form and integrate. That's the Jacobian formula, if you want. It's written in a kind of slick differential form way. Because phi t star of omega is Jacobian of the phi t times. Okay, so what we want to show, in other words, is that actually integral phi t star of omega over D is equal to integral over D of omega for all t. Right? We want to show this. This is the volume preserving property of the Hamiltonian flow. We have to prove this. Now, this is a quantity that depends on t. So if I want to show that it's equal to a constant, I better show that its derivative is zero. So we can look at its derivative then. ddt of integral by t star of omega over d, is it equal to zero for all t? Because if it is equal to 0, it means that it's a constant, and that value of the constant, of course, at t equal to 0, this is equal to that. So it means that it's always that. Now, what we proved using the fact that divergence of Hamiltonians is 0, and that divergence theorem version, the formula that we proved, shows that this is the case at t equal to 0. You see? So, yes, this is at t equal to 0. This is equal to integral divergence of h omega over d, but we know that this is 0, so this is equal to 0. So at t equal to 0, you're okay. But showing that the derivative of function at t equal to 0 is 0 doesn't mean that it is 0 ever. So what should we do now? We have to prove that derivative is 0 everywhere. There is a simple way out in this case. I mean, you use just the flow property, because there is some sort of translation property. I mean, there's a group property here. And I give you this as an exercise. The exercise is that we have phi T1 plus T2 equal to phi T1 corresponds to phi T2. This implies that the derivative is 0 into T of phi T star of omega is equal to 0 for all T, not just at T equal to 0. Because you can use this to translate everything again back to 0 by translating by a constant amount of T. It's not difficult. So proves the volume preserving property. I don't know how Liouville proved it. I have seen Liouville's papers on this. Actually, I forgot. I think, yeah, I don't know. It was not like this, because this Cartan formula is 20th century formula. So that really did a big shortcut for us. Liouville's calculations must be quite long. But I have seen proofs of this using, not using this Cartan formula, and it can take some time. It's not obvious. Yes. Any questions or comments? Mechanics as soon as possible. Very interesting. A few. I mean, you can spend 1 year teaching just this course. So many things. Just right now. Okay. So another thing we have to know about these things is about Poisson brackets. So let me just recall quickly Poisson brackets. Okay. So now for any f and g belonging to C infinity of 2n, we define a Poisson bracket G by the formula sum df dqi dg dpi minus df dpi dg dq from 1 to n. You see, we are taking of f as f of qi and pi and g also. So this is the Poisson bracket. So what are the properties of this Poisson bracket? Well, one is that this bracket is bilinear. Of course, it's bilinear. It's R bilinear. And is also antisymmetric. But there is another property which is not very obvious when you look at it, but it's the case. The third property is that it's actually a Lie algebra bracket. Plus Jacobian. So this basically what we're saying is that this defines a Lie algebra structure on this infinite dimensional space C infinity of R2. So giving a Lie algebra structure. But it has one more property that's also quite important. And that other property is that in the Lie algebra and the Lie algebra structure is compatible with the multiplicative structure, with the algebra structure. So 2 is that commutator of Fg and H is equal to F H times G plus F times G. So there is this sort of compatibility. It shows that multiplication is a derivation with respect to this Lie product, Lie brackets. So this is the Poisson bracket. So you might wonder what's the point of this Poisson bracket. So let me give some properties of this. First thing is there is something called Liouville's equation. It's very important. It's that rho from R to N to R be any smooth function defined on the phase space. Then what we can do, we can think of this as an observable on phase space, and we can look at so the points in the phase space are moving according to Hamilton's flow, and we want to study the variation of this rho along the orbits. So we're looking at rho of QT and PT as a function of t now only. So this tells us how the observable change as you follow the orbit, so you follow the dynamics. And in fact, it happens that the following lemma is true. Lemma is that rho dot is equal to commutator of rho, I mean the Poisson bracket of rho and H. This is called Liouville's equation. It's a bit like Heisenberg's equation in quantum mechanics. Heisenberg's equation is very similar, except you have operators here instead of functions, and instead of commutator, instead of Poisson bracket, you have operator commutators, and there is an IH factor. Otherwise, it's exactly the same thing. Proof. Well, I mean, what is rho dot? This is dBt of rho of Qt Et. So this is equal to, I mean, by chain rule or whatever, This is equal to d rho dq times q dot t. I don't put i's now. I can put i's, but I mean, let's put i's. And then plus d rho dpi dpi of ti dot. But we are over orbit. We are moving along the solutions. So qi dot is equal to dh dpi. That's equal to d rho dqi dh dpi. And pi dot is minus dh dqi. So this is minus d rho dpi dh. And this is the definition. I mean, this is sum, of course. Sum, and this is the definition of the Poisson bracket. Any question? Okay, so now something interesting we can derive from this, namely, if a function is such that this Poisson bracket with h is 0, then that function is a constant of motion. So the corollary, which is interesting, is that if you have an observable that Poisson bracket with h is equal to 0. Then this rho is constant, is a constant of motion. And these are important quantities because we want to know as many constants of motion so that you restrict the possible places where orbits can take place. Right?
In Lagrangian mechanics, the observables are just the functions of what observables are interested in that case?
Yeah, I mean, in that case, it could be functions on the tangent bundle, which is again
change in time.
Q and Q dot. Q and Q dot could be.
Oh, okay, that's what you
do. Yeah. But conservation laws in that case, like Noether's theorem, is a bit more complicated than this case. So this case is quite straightforward because there's a question of bracket. If this bracket vanishes, then it's a constant.
So Noether's theorem corresponds to, in some sense, the result in this formulation?
Yeah, I mean,
they both help you find constants.
Yeah, they both. Yeah, I mean,
more.
Well, I mean, I should not say that because it has to do with the action of a group, continuous group, like one parameter group of symmetries of the problem. It creates constants of motion. But this is something that, yeah, it's a constant of motion without having a group here per se. Although this rho, we can think of it. It also defines a vector field, and that vector field has a flow, and that flow is a symmetry. So in a way, this is kind of, I would say, this is really sort of maybe I think I can say is an analog of Noether's theorem in the Hamiltonian context.
Okay.
So we have to look more carefully. Off camera, but
okay.
But I think that there is something. I mean, in particular, of course, if you take rho equal to h, this obviously vanishes. H and H is 0. And again, you derive the fact that H is a constant of motion. Energy is conserved, which we also checked.
Yeah.
So it's a very special case. This conservation of, you get immediately you get another conservation of energy. Okay, so this is pretty good. But the full power of Hamiltonian mechanics is when, again, you go over manifolds. And the manifold that you have to consider in that case, so this is over manifolds. So these are, so now we are going to consider symplectic manifolds. What is a symplectic manifold? I mean, very simply, this omega is a two-form, is a differential two-form. I mean, this omega is non-degenerate, and is closed. D of omega is equal to. These are called symplectic manifolds. So the example, quintessential example, is if you look at and you go to R2n, you can take omega to be the following. Omega is equal to sum dqi with dpi minus so yeah, you can check that this satisfies all these conditions. Another example which shows what this is all about is when you have manifold and cotangent one. So when you look at the cotangent one, and in this case, there is an omega, which is d theta. So in this case, omega is already differential, is exact, is already differential over one form. So this condition of being closed is automatic. But what is theta? Theta is a canonical one form on the manifold, which in local coordinates we can write it as qi dpi. Now, what does that mean? It needs some thinking because it's not so obvious. What are the coordinates q and p? Well, I mean, q is a local coordinates. It's any coordinate on M, local coordinates on M. But this pi is the dual coordinate. So you see, you have to think about it. I don't want to do it now, but if you think about T star of M, there is a particular coordinate system. If you fix a coordinate system on M, it induces a natural coordinate system on T star of M, which we denote Pi. I just write it like this because it induces Pi. We have to spend some time to unpack the meaning of this. It's not obvious, but you can do it. Okay, so this is a one form. I mean, in this case, you can also look at it. But anyhow, let's go back to general case. It's always easier than example sometimes. So when you have a general, so now in general, that you're given this m and omega. So there is this, so then therefore any function h from n to r, we can still define this symplectic vector field xh. So what is xh? Xh is the following: you take dh, but dh is not good because dh is a one form, it's not a vector field. If you have a function, it's cheap to form a one form. It's always, you can do it on any manifold, you always get this one form. But you take this one form and then we just dualize it. I don't know how to do, this is the dual of pH with respect to omega. So what is this dual? Because what is omega? You see, omega is from T star of m at some q plus T star of m q to r, right? It's a bilinear form, right? Omega. But it's non-degenerate. So what does it mean? It means that it identifies cotangent bundle with tangent bundle. You can just take this, you get isomorphism, canonical isomorphism T star of m, T of m. So what you did, maybe you have seen in differential geometry with the Riemannian metric identifies vectors and covectors. This is the symplectic version of that. Because it's non-degenerate, you can always do that. So let me maybe give another definition. I mean, something completely related. So what is the property that we want? It's okay. So it has this property: omega of xh and any vector field y will be equal to dh over y for any vector field y. This also defines it unique by duality. Okay. So now you are in business. You have a vector field, so you can define this differential equation on the manifold. So, and that's Hamilton's equations. So you have classical mechanics on this symplectic manifold all of a sudden. Okay, so here we get this. Sorry.
Don't forget Camel.
You mean writing it in terms of equation?
So we get Hamilton's.
Oh, yeah. What is Hamilton's equations in this case? You're saying?
Right, and are we getting it from that formula?
No. That's more in. Okay, so let me tell you. So yeah, this is an excellent question. I was a bit. So by Hamiltonian system here, I don't mean those equations. I mean we have a vector field, and any vector field on a manifold defines differential equations. So you have the dynamics given. This is independent of coordinates. So through each point, if you give me an initial point in the phase space, I can find its future and its past following this. So the flow exists. I mean, but now what are those equations? What is the meaning of what? How can we produce those equations, Hamilton's equations that we had on Rn? Locally we can, but to do that we need some interesting result, which is called Liouville's theorem. Let me write it. That's not the trivial term. So yeah, that was a good question. So let me Liouville's theorem. Is X. I don't think it's S. I think it's X. Sorry. On any symplectic manifold, there always exist local coordinates. I mean, when we say local coordinates, I mean around any point, local coordinates, Qi and Pi, in which omega can be written as some dqi h. Isn't that amazing? It's locally, I mean, it's not locally. You can always write your symplectic two form as the canonical symplectic form on R2N locally. Hmm?
Yeah, like the 2 point that you could write out in spite of the
No, you can't patch them. And of course, it's not true that any two form can be written like that on a manifold. It's not true. I mean, you need coefficients here.
right.
If
But
you don't,
supposing it could be
in that coordinate you have, but over the manifold, you just have this, and then you have another one, but they don't match. These different coordinates, things get changed. Now, so this is quite important. I mean, for many reasons, it's important. So let me give you one reason why this is important. You see, symplectic and Riemannian, there are just two words. Symplectic is like an antisymmetric version of the Riemannian geometry, but they are so different. So I mean, so I'm saying omega versus Gij, metric. I mean, what is metric? Metric is a symmetric two form, right? It's a bilinear, non-degenerate symmetric two form. And what is omega? Is a nonlinear, is a bilinear, non-degenerate antisymmetric two form. So the difference is symmetric, antisymmetric. That's the difference. But for metrics, it's not true that you can write metrics of this in this form. G equal to some dxi tensor dxi. No, this is not true. This is only in Euclidean coordinates. If they exist, there's an obstruction for this, which is curvature. The curvature obstructs you, stops you from doing this. So this was studied by Riemann very carefully and found curvature, the obstruction to do this. But for symplectic manifolds, no, there is no obstruction. Always locally, so there is no symplectic curvature in this sense.
Sort of invariants that take its place.
Yeah, there are other invariants which are very
You're going to use like a kernel expansion to find variance on the symplectic manifold?
I don't know.
And also, is there a way to formulate symplectic manifolds in terms of spectral triples or some generalization?
No, unfortunately, that's not been done. I mean, so symplectic manifolds in non-complex geometry is so okay. So there is something has been done, but it's not. We are not there yet.
Oh, okay.
Yeah. So non-complex geometry has been very much focused on Riemannian, positive definite Riemann. Not even Lorentzian. Lorentzian even, although Lorentzian is symmetric, but non-degenerate, but a signature. Not this one. This is. I mean, okay. So if I wanted to give a course on symplectic manifolds and Hamiltonian mechanics, I would have spent at least maybe 2 weeks talking about symplectic vector spaces first, and then going over manifolds, and then so this is really all very fast. So I'm just trying to wrap up this classical mechanics because we want to go over quantum mechanics and quantum field theory. So yeah, there's always
more detail.
Yeah, you go into a descent, and then it's very hard to get out sometimes. Yes. So okay, I think so. We have so just to wrap it up, we saw 3 approaches to classical mechanics. That's not all. There are other approaches. So Newtonian mechanics, Lagrangian mechanics, Newtonian mechanics. There is one more which is quite interesting and important. It's very important also for classical mechanics. I'm not sure I will discuss it, but this is called the Hamilton-Jacobi equation. There's yet another equation which is called Hamilton-Jacobi. There's another equation which is very different. It's a PDE. So this we did not discuss, but it's an extremely interesting equation, and it's kind of closest to quantum mechanics. So it looks like you're studying a classical system instead of tracing the rays or orbits or paths of motion. You study classical dynamics by studying the wave equations. So how the wave propagates. Yeah.
Like classical wave.
Yeah, it's not wave equation. It's this Hamilton-Jacobi equation, but it's a PDE. So
solutions and elements.
So it gives you its constant values. It gives you wave fronts. That has to do with the approach to optics using that has to do with wave optics. Yeah. So that's and this was also discovered by Hamilton and Jacobi. So, but don't so some of the things that we did not discuss, you have to be aware of. Well, we didn't discuss Noether's theorem. We didn't discuss that. We didn't discuss Liouville's so integrable system. We didn't discuss integrable systems. Integrability. So let's call it integrable system. And Arnold-Liouville theorem. Another big theorem of Liouville. Liouville did a lot in mechanics, actually, in writing in mid-19th century. So Yeah, so this is, we didn't discuss that. Well, we did discuss a lot of things, really. Action angle variables in this case, for example. We didn't discuss adiabatic invariance. We didn't discuss. So, I mean, this can go on for 1 year. If I'm to teach, it would be 2 years. It will go on and on. So, but I mean, at least it's good to have some sort of impression of the scope of classical mechanics, which is really beautiful. Any question? I mean, certainly Darboux theorem I didn't prove, I just wrote a statement. Yeah, there are a lot. But we want to move to quantum mechanics soon and quantum field theory. Any questions? Comments?
You should teach a course on
Yeah, if they pay me,
that.
I am more than willing to teach. And if there are students, yeah.